All right. Graph sketching. It is, I think it's a thing that everybody remembers about calculus and advanced functions. This is kind of a long lesson, so just strap in. We'll try and go through it fairly quickly, and then I'll take some questions afterwards, okay? What we're going to be doing is we're going to be looking at this particular function, which is a rational function, and we're going to go through all the steps. We're going to find the x-intercepts, we're going to find the y-intercepts, we are going to find horizontal asymptotes, vertical asymptotes, any discontinuities, okay? We're going to determine how it approaches the asymptotes, whether it's they head to infinity, to positive infinity, or negative infinity, et cetera, et cetera. Then we're going to take the derivative. We're going to look for critical points, in other words, where the first derivative is equal to 0, or where the first derivative doesn't exist. And we're going to look for the intervals of increase and decrease. And then we're going to take the second derivative. We're going to look for points of inflection and concavity, okay? And that sounds like a lot. And this is a really terrible looking function. And so if you said, I really want to factor that function, that first thing you do is factor that function, yeah. Okay, so here we go. Let's factor it. This is exactly the equivalent function to 2x plus 1 and x minus 3 over, make sure you use your ruler. So this is going to be x plus 2, and this is going to be x minus 3. And isn't that nice? Okay, so we have some domain restrictions here. So x cannot be equal to -2, because that makes the bottom equal to 0, and that's just bad. And x cannot be equal to +3, because that makes the bottom 0, and that's just bad. But what's special about +3? Yeah, so this becomes one of those point discontinuities, okay? We can just cancel it out. As long as we're cognizant of the fact that the function doesn't exist there, we can now just treat it like this much simpler rational function, okay? So we've identified domain restrictions. What kind of a discontinuity is this, x plus 2? One of those, so this is going to be an infinite discontinuity. This is actually going to be a vertical asymptote when x is equal to -2, okay? So already we can go over here and we can draw in a vertical asymptote. How do you know that? Maybe a bit of an advanced functions thing, but when the bottom is going to 0, as you get closer and closer and closer to -2, the bottom gets smaller and smaller and smaller, okay? So like if x was negative 2.000000001, and I add 2 to it, I get a really small number. And the top divided by that really small number is going to be a big number, okay? So the limit as x approaches -2 from below and of the function is going to head for either positive or negative infinity, okay? Same thing as the limit as x approaches -2 from above of the function is going to head for negative or positive infinity, okay? Just as it gets closer and closer to that asymptote, it's going to head to infinity somewhere, okay? All right, so we have a vertical asymptote. It's here when x is equal to -2, and so we've already know something about our function. Let's do y-intercepts, because y-intercepts are fun. What is the value of x at a y-intercept? It is 0, so I'm just going to find out what f at 0 is, and that's 2 times 0 plus 1 all over 0 plus 2. And so there we go. I have a y-intercept, and it happens at 1/2. Okay, already I know something about what this function looks like. Okay. I want to know what my x-intercepts are. Okay. When I'm trying to find an x-intercept, that's when the y equals 0. That is just so great. So you guys who haven't taken advanced functions are probably just wondering, all you have to do is look at the top. When the top is 0, the whole function is 0. That's going to be my y-intercept. Okay, so I can just ignore the bottom, and I can look at 2x plus 1 being equal to 0, and that happens when x is equal to negative 1/2. Okay, so there we go. We have a y-intercept when x is equal to negative 1/2. Already we have 2 points. We have an asymptote as well. Okay, so there's our x and y intercepts, a vertical asymptote, and let's go after any horizontal asymptotes. Horizontal asymptote, it's got horror right in the name. Okay, just erase those domain restrictions. Now, there's this sort of abridged version that you get in advanced functions. The degree of the top is equal to the degree of the bottom, okay? And so there's a couple of approaches that we can use. Morgan, can you tell me what the horizontal asymptote is for this function? Nope. So there's a few ways of thinking about this, okay? One of the ways we already looked at, we can divide the top and the bottom by the highest power of x that we have in this rational expression. In other words, we can multiply 2x plus 1 by 1 over x, and x plus 2 by 1 over x, okay? And because I'm just multiplying by 1, I'm not changing it. We're actually trying to find out what the horizontal asymptote is. So we are looking for what value the function tends to as x heads for negative infinity and positive infinity, okay? So this becomes 2 plus 1 over x, and this becomes 1 plus 2 over x, okay? So the limit as x goes to negative infinity is basically going to be, this is going to be a small value, this is going to be a small value. So basically as x goes to negative infinity, this thing is headed for 2. Similarly, as x goes to positive infinity, I should put f at x, same thing, okay? It's basically 2 over 1, or 2. So we have a horizontal asymptote of x equals 2. So this is one way that you can do that. I'll just quickly show you a second way. The second way is a little bit more robust because it picks up oblique asymptotes. And of course, oblique asymptotes are, it's illegal to teach them in Canada, but hopefully the RCMP isn't, is it the RCMP? No, it's the OPP. It's illegal to teach them in Ontario. So we're just a little bit sticking it to the man here, okay? Anyways, you can see that as x gets really big, this just basically becomes 2 over 1, okay? Question becomes, it's approaching that horizontal asymptote, but is it approaching it from below or is it approaching it from above and all that kind of stuff? And we can actually skunk that out with our interval table. I'm just going to very quickly show you a second way that you can find the horizontal asymptote, and you can find the way that it approaches that horizontal asymptote, okay? Special gift from me to you. You're welcome. Okay, so here we go. This is 2x plus 1 divided by x plus 2. We're going to do that division as much as we can. Okay, so just remember, if we have 7 divided by 3, that basically comes out to 2 plus, and then I've got a remainder. So, you know, you say 2 plus remainder 1. And you guys are doing this in advanced functions right now, where you wind up dividing polynomials and you get a remainder. So this is like saying, oh yeah, 2 plus 1, and then you divide that 1 by 3 if you really want to finish it out. Take the remainder and finish off the division, okay? We're going to do the same thing, but we're going to do it with the polynomials, okay? So here we go. I've got x plus 2. And I know that I'm dividing it into 2x plus 1. So I'm going to find out what I would multiply by x plus 2. Putting x plus 2 into 2x plus 1. Okay. So I have to multiply x plus 2 by something in order to get 2x plus 1. And so there's a 2x goes in there, which means there's a 2 there, which means there's a plus 4 there. Okay. So I know that x plus 2 goes into 2x plus 1 2 times, but I only have 1 here. Here I've got plus 4, and so I know I have a remainder of negative 3. Okay, so you can do that by polynomial long division or synthetic division if you can manage it by synthetic division. For right now, though, don't worry about it too much. But basically what we're saying is this expression, 2x plus 1 over x plus 2, is equal to 2 with the remainder of negative 3 that still needs to be divided by x plus 2. Okay. So this can basically tell us what's going on as we're approaching this horizontal asymptote of x equals 2. Okay. So when x is a really big negative number, okay, like negative 100, this part of the expression is going to be negative, and we're subtracting it. Okay, so it's going to be positive. So basically, as x goes to negative infinity, this function is equal to 2 plus something small. Okay, because this is going to be, this whole term here is going to be added to 2. So that means we're approaching the horizontal asymptote from above. Okay. Same thing as x approaches positive infinity. 3 over x plus 2 is going to be positive. We're going to be subtracting it from 2. So this is going to be below, because we're going to be basically taking 2 and subtracting something small. Okay. Yeah, so sorry, I've drawn this at 2, but I didn't indicate it. Okay, so we've got a horizontal asymptote at 2 as x heads out this way, and I'd better erase that because that is just an artifact from before. Okay, we're approaching it from below, and as x heads to positive infinity, we're approaching it from above. Good. Hey, Maddie, how are you doing?
Good.
If you want to, do you have any questions?
I think I'm okay.
All right. Good luck.
Thank you.
If you want to, you can just turn off your microphone. If you've got any questions, turn it back on and feel free to ask me, okay?
Okay.
All right. Good luck.
Thank you.
Oh, sorry. What's the value of the y, the vertical asymptote here? What happens when x is equal to -2? Okay, so we've got a vertical asymptote when x is equal to -2. Yeah, that's right. Okay, there we go. Now, last thing that we're going to do with this function is we're going to make an interval table for it so that we can figure out when that whole overall function is basically positive and negative, and that is going to help us draw the rest of the graph. Okay, so exciting things are going to happen when x is -2. Okay, and we already know that. That's where our vertical asymptote is. And then exciting things are going to happen again when x is equal to -1/2, okay? And it's going to divide our positive and negative values into basically 3 intervals. One of those intervals when x is less than -2, and then when x is between -2 and -1/2, and then again when x is greater than -1/2, okay? So we've got our 3 intervals there. Exciting things are going to happen as far as sign changes go. I'm just going to erase this part, and we'll look at the value of each factor in each of those intervals. Okay, so 2x plus 1, one of the factors, x plus 2 is the other factor. There we go. Okay. Oh, I normally put these the other way on, but it's not going to make that much difference. Okay, here we go. When x is less than -2, x plus 2, it's really negative. And 2x plus 1, also negative. And so our function is actually going to be positive. Okay? When x is between -2 and -1/2, function is going to be positive. This is going to be negative. Okay? And so our function is actually going to be negative when x is less than -1/2. And then when x is greater than -1/2, both of these factors are positive, and that's going to make the whole function positive. And so now we have our positive, negative, positive of our function. Okay? So right now, you'll actually notice that I have these approaches to the asymptote. Yeah, I probably got them wrong. Okay? So when the function is between -2 and -1/2, it is negative. It's down here. And then when the function is greater than 1/2, it's positive. So my function's actually doing this, okay? Negative in this interval, positive in this interval. So it's actually approaching our horizontal asymptote from below. And the interval table gave that away, okay? When x is less than -2, the overall function is positive, and so it's got to be approaching that asymptote from that side, okay? And it's approaching the horizontal asymptote from above. So there we go. That's what we've got from our function so far. That's what we can just determine just by looking at the function. Now, believe it or not, this actually gets easier once we start taking the derivative. So the function actually simplifies, even though it looks like maybe it would only get worse. Okay. Does everybody have that? Good. Everybody looks really happy, so I'm glad. Okay, so let's take the derivative. This is the nice part. It breaks it up because we're going to be singing songs when we take the derivative. The derivative is going to tell us things like possibly turning points and critical points, and it's going to tell us if the graph is increasing or decreasing in particular intervals. Okay, so here we go. Let's take the derivative. And in this case, I'm going to use quotient rule because I think it's going to be a little bit easier. And so bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. There. Don't think I've made any mistakes there. Okay. Now we're just going to take that. We're going to do a bit of simplification. Okay. This becomes 2x plus 4. Oh, I'm running out of board space here. Okay, so it becomes 2x plus 4 minus 2x minus 1 all over x plus 2 squared. So this becomes 3 over x plus 2 squared. Look at that. That seems a lot simpler, right? Okay. Definition of critical points. we can identify them in two cases. When the first derivative is 0, so critical points, when the first derivative is equal to 0, or when the first derivative is undefined. Is equal to undefined? Could it be equal to undefined? I don't know. Okay, anyways, when is the first derivative, when is that ever equal to 0? No, nice try. It's undefined when x is -2. Okay. And when does it equal 0? Absolutely never. It never actually equals 0, so there's no turning points. Yeah. And if you look at what we've kind of got drawn over here, there's no turning points. But there is a critical point, and it happens when x is equal to -2. Okay? So, good for you for noticing that there was a critical point at x is equal to -2. So there we go. Here's f primed at x. And so what we're going to do, just going to make a quick interval table here, and exciting things are going to happen when x is equal to -2. So we're going to look at the interval when x is less than -2, and we're going to look at the interval when x is greater than -2, and we're interested in the sign of this function below and above -2. Okay. So here's the beautiful thing, the way this thing is simplified. When x is less than -2, this part in the brackets is negative, but because I square it, it's always positive. The top is positive, and so there we go. This thing is positive. Okay, let's go to the other side. Let's see what happens. Let's pick 0 because 0 is easy to add to 2. So 3 over 2 squared is positive or negative? It's positive, right? Look at that function. That is a function for a nice spring day. It's always positive, okay? And if the first derivative is always positive, what's true about the function? The function is increasing everywhere. Yeah, that's right. Okay, and if we look at what we have drawn already, look, everybody, this function is increasing everywhere. Everything is looking up, except for that part where we go to -infinity, but then we pick right back up again. So this is like an exciting function. There was, by the way, there was a little hole in there. I kind of haven't drawn it, but those little non-dimensional beings in flatland are going to be disappointed when they get to it. But for now, it's there somewhere. Let's just take a moment to remember it. Remember it? Is it at +3? Okay, let's put it in. We don't want to forget it. There. Okay, let's keep going. There's our first derivative. What should we do now? If you were saying to yourself, take the second derivative, pat yourself on the back. That is like, unless you've got a lot of chalk on your hands and you're wearing a black shirt, in which case don't pat yourself on the back. Okay. I'm going to rewrite this as a product because as much as I love the quotient rule, this is actually going to be just easier to write as a product rule. We'll do the product rule and the chain rule, and things are going to be beautiful. Okay. So, oh, sorry. That's not the second derivative yet. Hold your horses. Okay. 3 times product rule. -2 comes down in front. X plus 2. Take 1 away from -2. I think it's -3. Now, I do have to do the chain rule. Oh, yeah, we definitely do that. We're about to multiply the -2 and the 3 together, and you're welcome to do that all in one step. Okay, but I want to take the derivative of the inside of this function. What's the derivative of x plus 2? Yeah, that's right. Sorry, I just wanted to seem like I was overthinking it there. All right, okay, so this is -6, and that is over x plus 2 cubed. Okay, So we are going to determine concave up and concave down using this system. And what should second derivative determines if it's concave up or concave down, and it can switch concavity when the second derivative is equal to 0. And what value of x is this second derivative equal to 0 for? Absolutely nothing. Yeah, there is no value for which it's equal to 0, but we do have a place where the second derivative is undefined, and that is when x equals -2 again. Keeps popping up. Maddie? Does somebody have a question? Oh, okay. All right. Thought somebody said Mr. Rogers.
I did, sorry, I was still muted. For question 2, you have the chromium diagram, and then you ask for copper shorthand. Did you mean to ask for chromium shorthand? Because the next page is copper.
Yeah, probably I did. Yeah.
Okay, so I should do chromiums on that page?
Yeah, that's right.
Okay.
Thanks, Maddie.
Thank you.
Okay, here we go. Hey, what should we do, Morgan? Make an interval table? Yeah, okay, good. Exciting things are going to happen when x is equal to -2. So here we go again. X is equal to -2. A lot happens around x equals -2 with this function. Okay, so x is less than -2, and -2 is less than x. There we go. Okay, and we're interested in the value of the second derivative. Okay, so this has got a negative sign out in front of it, so we just have to just remember that negative sign, okay? Okay, x is less than -2. What's the bottom? Negative. Yeah, that's right. Yeah. So x plus 2 is going to, yeah, which makes the whole thing positive. Look at this. Look at this function. It's so positive. Even when things are negative, this function is positive. Okay. So let's go. X is greater than -2. I hope this function pulls through for us. X is greater than -2, so like 0. It's positive, except there's a negative there, which makes it negative. Oh, the function finally let us down. Okay. But we have determined concavity. It is concave up when x is less than -2. And when x is greater than -2, it is down, concave down. That's right. Concave down. Okay, good. And we can see actually with this nice rational function that looking at most of the stuff, most of the information actually came from the function itself. Okay. There you go. That's it. We're done. So that is the graph sketching algorithm that everybody learns. And I don't know how many minutes it was, but I'm hoping it was like less than 20. Okay. So function itself, x and y intercepts, vertical asymptotes, horizontal asymptotes. Was there something else? Discontinuities. Okay. First derivative tells us increasing or decreasing. Okay. And it can tell us turning points and things like that. You're making interval tables as you go along. All right. Second derivative, we're looking for concave up, concave down, all that sort of stuff. Okay. That's the algorithm for curve sketching. I'm going to stop broadcasting right now.